Alright. So today I wanted to teach you guys L'Hopital's rule. And there are three what we call indeterminate forms. And then there's another set of forms that are sometimes called indeterminate, but I like to call them something else. We'll try to come up with something here. Because indeterminate, these three forms that you get, infinity over infinity, 0 over 0, or minus infinity over infinity, those are really the only three forms that tell you L'Hopital's rule can be used right now. The other forms say L'Hopital's rule can be used, but you have to decide how to make it be usable there. And the key to it really is, if you notice, it's got to have a rational expression, right? I've got to have a function over another function. If I don't have that, then I can't use L'Hopital's rule. And the idea, and we have to suspend what we've done so far in terms of taking derivatives. The idea is, if we evaluate a limit and we get any of these three forms, then we better go ahead and take the derivative of the top and the derivative of the bottom. The key word here is separately. So we do not differentiate them at the same time. So it's not a quotient rule that we're doing, but instead differentiating the top by itself, the bottom by itself, and then evaluating the limit. Alright, so let me just demonstrate. This first one here says e to the x minus 1 plus sine x over 4x. So if I plug 0 in there, right, it says the limit as x goes to 0, what happens? Well, that's e to the 0 minus 1 plus sine of 0 all over 4 times 0. E to the 0 is 1. So 1 minus 1, they cancel. Sine of 0 is 0. And 4 times 0 is 0. So you end up with 0 over 0 for that. Which means that is an indeterminate form. And L'Hopital's rule says take the derivative of the top and the derivative of the bottom and evaluate again. So let's do that. So if I take the derivatives here, this would be limit x approaches 0. Derivative of e to the x is e to the x. Derivative minus 1 is 0. Derivative of sine is cosine. And derivative of 4x is 4. Now evaluate again. So plug in. This is e to the 0 plus cosine 0 all over 4. E to the 0 is 1. Cosine of 0 is 1. So we get 1/2 out of that. So that's the limit of that that expression using L'Hopital's rule. So let me come over here and do this one. This one says plug in pi. So if I plug in pi right now, cosine of pi is -1. -1 plus 1 is 0. So again, we get 0 over 0. So, L'Hopital's rule says take derivative of top and derivative of bottom separately and evaluate again. So derivative of the top, I get minus sine. Right, derivative of 1 goes to 0. Then I need derivative of this whole bottom here. Well, that would be 2 times this to the first power. And then the derivative of the inside would just be 1. So that'd be this guy. So evaluate again. Minus sine pi over 2 times pi minus pi. Pi minus pi, that's 0. Sine of pi, also 0. So look, we got 0 over 0 again. That's okay. We can apply L'Hopital's rule as many times as needed until we get to some answer. So let's do it again. Derivative of minus sine. It's going to be minus the cosine. And then derivative down here is going to be 2. Or if you really want, this is 2x minus 2 pi. So derivative just gives you 2. So plug in pi again. That is minus a negative 1 over 2, or once again, 1/2. All right. Any questions so far? So first thing with this one, I'm going to plug all the zeros in. Sine of 0 is 0. So this whole thing is 0 over 0. That's one of those indeterminate forms, so we can go ahead and use L'Hopital's rule. So take the derivative. So derivative of sine is cosine. This one you have to use chain rule, so you get a 2 out in front. Derivative of sine is cosine. Derivative of x is 1. Derivative of sine, cosine. Plug in 0 again. So if I plug in 0, cosine of 0 is 1. This one's also going to be 1, so up top you get 2 minus 2 all over 1 minus 1, or 0 over 0 again. So we've got to take another derivative. And another thing is, I should have done this anytime you use L'Hopital's rule, write the equal sign and put a little h over it. So let me go back and do that. That just indicates that you've taken a derivative and you're going to evaluate again. So taking derivatives, derivative of cosine is minus sine. Derivative of cosine there is also going to be minus. There's already a negative, which makes it plus, and you get another 2 out in front. And then on the bottom, 1 is 0. Derivative of cosine becomes minus the sine, and there's a negative, so it becomes plus. So plug in again. Everything is a sine, so everything goes to 0. So it looks like we've got to do one more L'Hopital rule. Now derivative of cosine is going to give us 1. So we get minus 2 plus 8 all over 1, or 6 for that limit. There you go. So L'Hopital's rule is not hard. It's just maybe a little tedious. There are, like this last problem we just did, you got to plug in a lot, or take the derivative many times. So let me erase this so I have some room. I wanted to do another one that did not result in 0, 0. Erasing very well. Terrible. Come on. All right. Oh, that was such a bad marker. Alright, so I wanted to demonstrate one that came out as infinity over infinity. So we had the problem yesterday. Let's see if this marker works. That we had natural log of x over x squared as x went to infinity. So if we had that, this would be infinity over infinity. So that's another form that says you can go ahead and use L'Hopital's rule. And so you take the limit as x approaches infinity. Derivative of natural log of x is 1 over x. Derivative of x squared is 2x. If you simplify that before plugging in, you get 1 over 2x squared. And then if you substitute this in now, this is 0. So if you get 1 divided by infinity, you can say that's 0. So that's just an example where the derivative is not, or the original limit isn't just 0 over 0. It was something different. All right. So as I said, there are other forms. So we had the 0 over 0, infinity over infinity, and it's okay to have minus infinity over infinity. These forms also allow you to use L'Hopital's rule, but you have to rewrite the equation before you can do it. So you might not recognize what these two functions do at 0. But if we rewrite them as their counterparts for trig, this is 1 over sine minus cosine over sine. Now if I substitute 0 in there, sine of 0, that's 0, and this is also going to be 1 over 0. So all these years we've been saying can't divide by 0, but here in calculus we're going to start saying that 1 over 0 is infinity. And if you think about it, right, it's 1 divided by a really small number. So that gets to be a really big number. So that's one of the other forms. We've got infinity minus infinity. So that tells us you can use L'Hopital's rule, but there is no top and bottom yet, right, to differentiate. So I've already written them out. Right, it's pretty clear that they have a common denominator, so I could put them together. So this is really the limit as x approaches 0 of 1 minus the cosine over sine. Now if I substitute 0 in, I get 1 minus 1 over 0, or 0 over 0. That's one of those indeterminate forms that says, okay, go ahead and use L'Hopital's rule now. So differentiate top and bottom separately. So derivative of 1 minus cosine is going to be sine, and derivative of sine is cosine. Now if we substitute, we get 0 over 1. And here's where things get weird, because people are confused by 1 over infinity and 1 over 0. So 0 over 1, well, that's just 0. and that's okay. So limit of this function is 0. All right, here's another one. So this is x squared e to the minus 2x. If I try to plug infinity in there, x squared, well, that's really just infinity. And then e to the minus infinity. Well, that's really like that, 1 over e to the infinity. And that's just 0. So we get infinity times 0 here. So that's one that's actually not listed up here. But that is yet another form. And so I just need to rewrite this thing to get some 0 over 0 or infinity over infinity. So to do that, I'm just going to take this e to the minus 2x and put it in the denominator. Just by doing that, when I substitute infinity now, I would get infinity over infinity out of this thing. And so I've created a situation where I can go ahead and use L'Hopital's rule. So I would differentiate top and bottom. So that would be 2x over 2e to the 2x. Those would cancel. You plug in infinity again. You get infinity over infinity. So we just have to do it one more time. So derivative of x is 1. Derivative of e to the 2x is 2e to the 2x. So we would get 1 over infinity or 0 again. Any questions about those? And I noticed some of the viewers have been fluctuating. Is anybody having any trouble connecting today? So there's 2 more of these type and then one other kind that I can do for you. And then we'll try a few optimization problems. And then of course I'll do that other problem I had promised to you guys. Alright. So again, let's plug in, see what we get. Plug in 0 here. So this one's 1 over 0 or infinity. Cotan is really cosine over sine. So that's going to be 1 over 0 again, or infinity. So this one gives us infinity minus infinity. So once again, we just got to get a common, or get a denominator here somehow. We could do that by getting a common one. So I'm going to rewrite this as limit x approaches 0. As we said, this is cosine over sine. So put that together. So I need to multiply this by x, multiply this by sine. And then on the bottom, my denominator will be x sine x. Plug in again. So this is going to be 0 times 1, so that whole thing's 0. That'll be 0, and this will be 0. So we get 0 over 0. So we can use L'Hopital's rule by taking the limit and differentiating top and bottom. This is a product. So that would be minus x sine x plus derivative of x is 1 and leave the cosine alone. Derivative of sine is cosine. All over. Derivative of x is 1. Then leave x alone. Take derivative of sine. So we've got cosine x minus cosine x. We can get rid of those. So just rewriting. Then substituting 0 in. So this would be 0 over, and these would both be 0. So that tells me I need to do it again. So product up here once again. Okay. And then I see I've got a cosine plus cosine down here, so I'm just going to make that two cosine. Plug 0 in again. Well, that's going to be 0, that's going to be 0. That's not going to be 0 for once, so that's good. So on top we have 0. And on the bottom, we're going to get 2 minus 0. So we get 0 out of that. Alright, last one of this type. Plug 0 in over here. 1 over 0 is infinity. Cosecant is 1 over the sine. That's also going to be infinity. So rewrite the whole thing. Then simplify by putting the two together. Plug in the 0. Turns out we get 0 over 0 again. let's go ahead and differentiate and use L'Hopital's rule. Derivative of sine is cosine. Derivative of x is 1. And on the bottom we have a product. Comes that. Plug in 0 yet again. We're going to get 1 minus 1. 0 plus 0. And it all results in 0 over 0 again. So that says go right ahead and use L'Hopital's rule. So let's do it again. Alright, cosine x, derivative is going to be minus the sine. And on the bottom, this is going to give me another cosine, so I'm just going to make this plus 2 cosine. Right, so I would get a derivative of x is 1, that would give me a cosine, and then I would get a plus cosine out of that one. Alright, substituting again, looks like 0 over 0 plus 2 again, or 0. It's not too tricky, you just got to be efficient at plugging in values in the trig functions and taking derivatives of products and things quickly. So before I erase these, any questions? Alright, so let's go ahead and get to that last part of L'Hopital's rule. How did you get to sine minus x over x sine x? I'm assuming on what I just erased, unfortunately. So that was just taking derivatives. Are you thinking that I took one incorrectly, or you just weren't sure how I got it? Oh, that was okay. So that was the start of the problem. Cosecant is 1 over the sine, so I just wanted to get a common denominator. So, right, if this is 1 over x minus 1 over the sine, I can multiply the first equation by sine over sine, and the second equation by x over x, and then I get sine x up here minus x all over x sine x. Hopefully that answers your question. All right. Yep, no problem. Looks like I missed a spot. Alright. So this last section of problems is slightly different because we've now got a power here of 1 over x. So first thing you should always do is try to direct substitute. So if I did that, this is 1 minus 3 times 0 to the 1 over 0. That is 1 to the infinity. So that again, there's a little bit of a glare there. You can still see it though, okay? 1 to the infinity. That's one of those other forms that says it's okay to use L'Hopital's rule, but we haven't got it in the right form yet. So somehow I've got to get a fraction out of this thing. Well, the only way we know how to get this guy down is to take natural logs. So I'm going to say let y equal the limit then I'm going to take the natural log of y. And remember that the limit is weird in that the limit can go in and outside of logs. So I can actually take the log inside here. I'm going to kind of forget about this side for a second. That allows me to bring this 1 over x down. So if I chose, I could, instead of writing 1 over x, I could write natural log divided by x. So when I do that, plugging infinity in, natural log of infinity is infinity divided by infinity. So I've successfully gotten it in a form that tells me I can use L'Hopital's rule. So I just need to differentiate top and bottom. So derivative of natural log is 1 over the inside, and then we need times derivative of the inside. So that's minus 3. Differentiating x, that's just 1. So now I need the limit, so x approaches infinity, of negative 3 over 1 minus 3x. So now if I substitute infinity in down here, the bottom is approximately infinity. So I have negative 3 over infinity, which heads towards 0. However, that's not my final answer because the original problem was y, not natural log of y. So this results in natural log of y equals 0, or taking e of both sides, y equals 1. Y is the thing that I called the original problem. So my answer is actually 1. So I'm guessing there might be a question about that. So I'll give you guys a second to take that in. make sure I didn't I put the wrong bound in. That's what happened. Okay. So let's reset here. Nothing wrong with what I did, but that would be if the problem was to infinity. It was originally to 0. So let me just replace these bounds. Nothing really is going to change except for when I plug in here and there. So if I plug in right here, this goes to 0. Natural log of 1 is left behind. And then I have 0, so I get 0 over 0. Still an indeterminate form. And then when I plug in over here, I'm going to get negative 3 over 1, or negative 3. So this would equal negative 3. This would be e to the minus 3, or 1 over. And so my final answer would just be 1 over e cubed. I'd done the problem yesterday and thought it looked strange, and it was just because I plugged in the wrong limit, that's all. But that wasn't too bad. It just gave you another example, really. Everybody good? So, go ahead and do another one. All right, same type of problem. Notice this does say from to 0 from the right. Not a big deal. When you do direct substitution, you would still plug in 0. So I got to do the same thing. I'm going to call this y. And I'm going to take the natural log. Put the limit in front. Just trying to make sure the glare is not too bad there. So let me ask you guys this. How would I turn this into a fraction? What would you do? No clues, I guess. So you would take the cotan, right, which is cosine over sine, and make it 1 over the tangent. So now if we plug in 0, we still get natural log of 1, and on the bottom, tan of 0. So that's 0 over 0, which is good. That means we can use L'Hopital's rule. So derivative of natural log is going to give me 4 over 4x plus 1. Derivative of tangent, secant squared. Plug in 0. Secant is really 1 over the cosine. Cosine of 0 is 1. So secant squared is just 1. So we get 4 out of that. But recall that this is equal to natural log of y. So natural log of y equals 4. Means y equals e to the 4th. Because you would raise both sides e. And that is your answer. So the cotangent, right, that's just, cotan is cosine over sine, and tan is sine over cosine, so it's 1, right, this is the inverse of tangent, or 1 over the tan, just like cosecant's 1 over sine and stuff like that. So I just use that relationship to be able to write cotan as a function that you would put in the denominator. Alright, so let me go ahead and finish up this last one. And then I will start optimization, because I think we'll probably need 2 sections to get that done. So I'm curious, who all is with me this morning? So I know I saw Shelby and Jonathan, and I think Mike. Who else is out there watching? Caitlin, yes, sorry I forgot. Shriyam, good morning. Nice. Alright, so let me go ahead and do this guy. If we plug 0 in, right off the bat, that's 0 over 0, or 0 to the 0. That's one of those strange forms that says it's applicable, but we've got to get it in the right form. As always, I'm going to let it equal y and take the log. And again, the log allows me to take this x and bring it down in front. And this one always really confuses people. So I've got an x here. How do I get this x to somehow be in the denominator? Well, if I have, say, 2/3, well, that's the same thing as if I had 1 divided by 3/2. Morning, Naya. So I could take some number and make it 1 over the inverse. So here I'm going to do x is the same thing as saying 1 divided by 1 over x. So that looks really strange, but think about it for a second. Right, 1 over x, I would flip and multiply it. And I would just get x back. So this is, albeit a strange way, but an effective way to rewrite x. So I can come over here and I can change this to natural log of x divided by 1 over x. Because divide by 1 over x is the same thing as multiplying by x. Now I had to do that because I've got to get one of those indeterminate forms. So if I plug 0 in, right, natural log of 0 is negative infinity. And you're probably going, well, how in the world did you know that? Well, natural log function looks something like that. So if x is approaching 0, right, this thing's heading off towards minus infinity. And then 1 over 0, well, that's infinity. So we get infinity over infinity, or minus infinity over infinity, which is great. That tells me I can use L'Hopital's rule. I'll come over here. I need to differentiate natural log. That's 1 over x. The derivative of 1 over x is minus 1 over x squared. If you need, rewrite this as x to the minus 1 to get this. Another mistake that people do a lot is they'll try to plug in right now. Well, you'd get infinity over infinity again and think you'd have to take another derivative. But you don't need to do that. If you just simply put these two together, you can apply the limit. So this is really 1 over x, and then negative 1 over x squared, I can multiply by its reciprocal. And that's just going to simplify to negative x. Plug in 0. This guy is 0. But the last step is you have to remember that was equal to natural log of y. So natural log of y equals 0. Take e of both sides. Y is 1. And y is the original statement. So that is your final answer. Any questions about that guy? All right. Doesn't look like you guys have any questions. I'm going to go ahead and erase this, clean up the board a little bit, and do a couple optimization problems. This is being such a pain today. So while I'm doing this, how's everybody doing? Looks like we have a wide range of emotions right now. All right, darn this board. All right. So optimization. We have two equations, and our job is to optimize the preliminary equation And the secondary is just one that we create from the data given, and we're going to plug it into the preliminary. So there's just a bulleted list here. It says to find those equations first, solve for one of the variables in the secondary, and substitute into the primary or preliminary. I'll probably say primary more often. Determine the feasible domain on the primary equation. That's one thing I often forget to do, so if I do, remind me. Find the derivative of the primary equation and find the critical values. Right, so we're trying to optimize, which really means to maximize or minimize something. And as soon as you hear max or min, your first thought should be differentiate, set to 0, and find the critical values. And then finally, find the solution using the feasible domain and those critical values. So obviously your solution has to fit within the domain of the function. If it doesn't, then it's really not the solution you were looking for. All right. So the first one here says find two positive numbers whose sum is 110 and whose product is a maximum. So when we say two numbers, right, we typically use variables for those. So sum is 110. So I'm going to say x and y, and they have to add up to 110. Then it says their product must be a maximum. So the product is x times y. So over here in the chat, tell me which one you think is the primary and which one's the secondary. Or you could really just say one, and then obviously the other has to be the secondary. All right, so I got one answer. Anybody else? So we've already got both of them. Let's get one more person to say something to try and break the tie here. All right, so it actually is the p equals xy, all right, because that's the thing we're trying to maximize. That's the primary equation. This is the secondary, right? It said that the secondary equation has some data given to us in the problem. That's that 110. So this is primary. So I need to solve for one of the variables here, plug it in down here. Doesn't matter which one. I'm going to solve for y. It's 110 minus x. I'm then going to substitute that in. So p equals x times 110 minus x. If I'm trying to maximize this thing, I have to differentiate it. So dp, this is going to be dx. And I'm going to set it to 0, so I don't really care what this is over here anyway. We can go ahead and multiply this in to make it a little easier on ourselves instead of having to do a product. And then the derivative of 110x is 110. Derivative of this is going to be minus 2x. Solve this for x. Move this to the other side. And divide by -2. So 110 divided by 2 is going to be 55, right? And if x is 55, we can plug it in right there. And we get y. So it just so turns out that x and y are both 55. So I wanted to prove something to you here. If you guys have your calculator, do me a favor and do 55 times 55 and tell me what you get. And then I want somebody else to do 56 times 54. And then 57 times 53. All right, so this is 30, 25. So somebody else do this one. All right, 30, 24. And then you're saying this is 30, 21, okay? So that should prove to you that these two numbers that add to 110 have the highest product, because I started taking one away from this one, or adding one to this one and taking one away from that one. Still adding to 110, my product's slightly smaller. And then taking another one away and adding it to the other, still a sum of 110, product's even smaller. So we found the two numbers who add to 110 and have the largest product. So that's interesting, right? I hope. But it might not be necessarily something that you would just come up with as an everyday problem. So let's try another one that has maybe a little more application. Another thing people often ask me is, how do I know if I'm maximizing or minimizing an equation? We really can only do one. So I always found it kind of silly. It should say to make it an optimum and then ask what kind, right? Because when you ask the question, you already know if it's a max or a min. So if it's a certain type of function, you could tell that, right? If it was say a parabola and it was a negative x squared term, that's going to have a maximum. But if it's a normal parabola with an positive x squared, that one's going to have a minimum. All right. So I might do this one and then leave the rest for tomorrow, or for, not tomorrow, but Monday. So this says 24 inches by 18 inch box is, all right, so let me change that wording. That should be, instead of box, let's say piece of cardboard. So we've got a sheet of cardboard. It's 24 by 18. And we're trying to construct a box by cutting out 4 equal squares from the corners. What are the dimensions of such a box that will maximize the volume? And what is that volume? So, let me just draw the situation so it makes sense. Right, we've got a sheet of cardboard. And it is 24 by 18. I'm then going to cut 4 equal squares from each corner. So if you think about removing these pieces, then you could fold these two sides, right? If you fold on these creases, and that would create a box without a lid. Does that make sense to everybody? All right, good, thank you. So I've got this. I want to maximize my volume. So I need a volume equation. I'm going to call the length that I cut here x. So that's all of these sides. So now to get the volume of the box, I need this length, and this length. All right, because this is the bottom of the box, so it would have length times width, and then this distance right here would end up being the height. So we know that the volume is length times width times height. For the length, let's call that this side, I guess. This side will be width. So the length, this section, is going to be the total distance here, 24, minus that x and minus that x. So this length is going to be 24 minus 2x. The width is going to be 18 minus x minus x. And of course the height is x. Is everyone okay with all of those? So these are my, oof, what was that? Secondary equations. Which looks like you can barely read. So I'm plugging all of these into this. So this is 24 minus 2x, 18 minus 2x, and x. I notice there's a 2 in common everywhere, so I'm going to pull that out of this and this. So this is 12 minus x, and this becomes 9 minus x. Now, why did I do that? Because I want to talk about the domain. So, in this equation, the smallest value of x that I could plug in would be 0. Right? Because I could plug 0 in everywhere and it's fine. Doesn't make sense to have 0 length, but I can plug in 0. It's okay with the function. And then the biggest numbers I could plug in, well, here if I plug in a number bigger than 12, this becomes negative. And I can't have a negative volume. But here, if I plug in anything bigger than 9, I get negatives. So I can't be bigger than 9. So whatever the answer is that I get has to be somewhere between 0 and 9. So I'm trying to maximize the volume, which means I have to take the derivative. So I need to find dv dx, and I need to set it to 0. I think I'm going to go ahead and differentiate it in that form. So I'm going to take the derivative of 4x, that's 4. Leave the other two alone. Plus, derivative of 12 minus x is a minus 1. So this is going to be minus 4x times 9 minus x. And then derivative of 9 minus x is going to be a minus 1 again, so minus 4x times 12 minus x. So then I could divide everything by 4, get rid of that. And then I think that's about as much as I can do besides going ahead and multiplying this out. So I just need to know what is that multiplication. So that's 108. Then I'm going to get minus 12x minus 9x plus x squared. I'm going to get another minus 9x plus x squared and a minus 12x plus x squared. So simplifying, and you don't have to do it this way. You could have multiply this all out at the beginning and then took the derivative, and you should get the same result. So it looks like I've got 3x squared, and then (42) minus 42x and plus 108. So does 3 go into 108? Okay, does it go into 42? Sweet, so let's take out the 3. So this is x squared minus 14x and plus 36. So that's something we can handle pretty easily. We're looking for two numbers that multiply to 36 and add to negative 14. So can anybody think of those factors? It doesn't actually look like that's factorable, unfortunately. So we've got to use the quadratic formula. So x equals 14 plus or minus square root minus 4 times 1 times 36. That's going to be 144 all over 2 times 1, or 2. So let me check that. Yep, 144. So 14 plus or minus square root 52 all over 2. 52. It's got to have a perfect square hidden in it somewhere. Four. So that would be 14 plus or minus 2 square root of 13 over 2, or 7 plus or minus square root of 13. So let's see what square root of 13 is. It's 3.6. So the plus square root of 13 doesn't fit within our logical domain. That would be 10.6. So only the 7 minus works. Only the 7 minus root 13 fits in the domain. It is approximately 3.39. But I'm going to continue to use this form, the 7 minus root 13. So it says, what is the volume? Well, we've got to plug that in everywhere for an x now. be 4 times this times 12 minus, off the screen, almost. You could also plug these in separately into the length, width, and height, and then multiply those three things together. I'm going to attempt to plug all of this in into the calculator. So multiplying all that together, it's 654.977. So it says it's a little hard to read. I'm assuming you're talking about this guy over here. So I just plugged in 7 minus root 13 into this equation everywhere I saw an x. So this is 4 times 7 minus root 13, 12 minus that, which gives you 12 minus 7 plus root 13, and then 9 minus 7 plus root 13. So I need to try and revamp this problem with hopes that it would come out with nice numbers. Either way, are there any questions about how I got to that volume? All right, I set up the equations for length, width, and height, multiplied them all together to get the volume, differentiated and set to 0 because I want to find a maximum. I took this and solved with for the quadratic formula, and figured that only one of these fits in the feasible domain that we came up with, which was from this equation here. You would have gotten the same thing had you tried to do it here. And then finally I just took that, plugged it in here, and got my volume. So that's the last one of these problems I'm going to do for you guys today. If you want, I can do another one of the graphing problems. Does anybody have a particular one they want to see? If not, I can grab one out of the textbook real quick. Ugh. I'm a pain today. I don't know why it was working so well, and all of a sudden it just started getting bad again. Damn. like I spent half the day erasing the board. Alright. So I'm going to go ahead and stop the recording for the day.